Hi, can everyone hear me? Sorry about that title. I should have made that a little bit more friendly. Sorry, is it just it? Okay. So I'll try to make the talk a little bit more friendly than this. So let's see what are monoclonal antibodies. Basically, all of us in this room at some point might have gotten sick, and then we also got better, and that's the reason why we're all here today. So one of the things that happens when you get sick is that your body is attacked by a foreign particle, which is then identified as a pathogen, and the immune system gets activated. And this immune system then generates antibodies to fight the disease, and that's how we get better. So humans being really smart, we thought, okay, why do we have to wait for the body to generate these antibodies? Because there is a downtime related to that. Can we just create these antibodies in a different animal and then extract it and then use it on humans, which makes it much faster? And this is great, but then there are like certain problems with this, one of them being biocompatibility. Because if you're doing it in a mice, maybe it's not compatible with humans. And then we thought, okay, so if we can do it in an animal, maybe we don't really need an animal. We could just use some cells in a lab to culture these things. And that's how we went from there to producing them in labs. And this is a really powerful technology because once you can produce them in labs, you can produce antibodies for any kind of disease. Sometimes your body cannot really generate antibodies against certain diseases that are, that we don't recognize, or sometimes we cannot really identify the pathogen itself. So in these cases, you can generally actually generate one in the lab and then distribute it. This is a really great technology, but then you cannot really grow them in like 20 ml flasks and give it to the whole world. So definitely you have to scale this up. That's where large-scale bioreactors comes into picture. So you have these large-scale 500-liter bioreactors where you grow them in like really large scale and distribute. So if we have all of this cool technology, then why is it not really available to all of us for use? Can I just walk into a GP's office and say, hey, doctor, I have a problem. I have a flu. Can I just get an antibody treatment? No, this is not happening. So why is it not so commonplace? So you might probably remember from the time during COVID that Donald Trump received an experimental antibody treatment, and he seemed to be doing fairly well. Oops, I meant health-wise. But so the main reason it's not accessible is because of the cost of these treatments. So the main, even for a single dose of antibody treatment, it costs like 3,000 to 5,000 pounds, which is not really affordable to a large fraction of the population. And the main reason for this is because of the manufacturing cost. So even generating an antibody itself is very expensive. In addition to that, scaling up this is like a really expensive process. The main reason being, you have these large-scale bioreactors of 500 liters, which you have to run for a period of 14 to 16 days to even get like a really small amount of product. And sometimes you end up with like grams or milligrams worth of product. And this is really not lucrative for the companies. And this is how the price gets transferred to, like it gets passed down to the customer. And that's why these products are really expensive. So somewhere in there, we have a biology problem, engineering problem, which we can identify. Because you see, the only way we can actually make this really accessible is by actually, increasing the productivity or the outcome from these bioreactors. But the problem here is that once you actually set up these bioreactors, they're going to run for 14 to 16 days, and you really have no idea what's going on inside them. You can really measure some of the variables, but then you don't know by just looking at those variables what's going on inside the reactors, and if you want to change something or if something is going wrong, and if something is actually going wrong, how do you change it or how do you salvage these cultures? There is no idea of how this can be done. That's why we identified this as an engineering problem and tried to tackle it. So a bioreactor, although it looks very much like a chemical reactor, is fundamentally very different because you're growing live cells in them. And then there is all the outcomes that we see as a response that we observe is because of the dozens of variables that interact with each other. But then one of the fundamental problems with this is that we don't really have an understanding of the process dynamics that's going on inside these cells. So the controllability factor is really limited, because if we cannot control them, we don't know how much product they're going to generate. So this is why we thought, okay, this, if we have some data, maybe we can learn about these cultures from past data, and then maybe we can design better control actions for these. So for example, variables such as pH or temperature, we generally know what kind of pH they cells like or temperature they like, but we really don't know about rest of the variables that we can measure. So this is why we thought, okay, maybe we can think about it as a data science problem and an engineering problem at the same time, but then it also has a lot of biology behind it. Now, if you know what values certain variables like, you can generally do a set point control, which basically means you tell the controller, okay, this is the value you want it to, and if it goes above or below that level, the controller would take an action. But then if you don't know that, then what do we do? So in the literature, you would come across equations of this sort, which are very generic, which are highly specific for a particular type of cell type or product type or antibody product type, things of that sort, which is not very useful because if you're thinking about a large-scale bioreactor, you will grow all kinds of cells in them, and you want to find a mechanism that will work for a lot of different types of cell types. So this is why I thought, okay, we need to really understand the cell dynamics before we can develop a control system. So this is where we thought, okay, we need to go to the basic biology. So if you have taken biology in school, you probably remember that cells have a different growth phases, which is basically a lag phase, log phase, and a stationary phase. But what we don't often think about is that this is because of all the variable interaction that happens within and outside the cell. And if we know these variable interactions and we know how they relate to the outcome, maybe we can design those interactions to get the outcome that we want. And that's exactly what we wanted to know. We wanted to learn more about these interactions. And the easiest way to learn about interactions is through networks. We heard in a previous talk about networks. So basically, network is very straightforward. You have nodes, which are basically entities, in this case, different variables, and then you establish an edge between them if they are interacting with each other, and then you assign a weight depending upon the strength of the interaction. So once we have these kind of interaction networks, it's very useful because then you can extract a ton of properties from them. For instance, you can identify from a property called centrality, a key variable on a specific day. This is very important because if you're trying to develop a control action, you need to know what variable is important because then you would control that variable. And then there are properties such as shortest path, which will tell you which variable to target. For example, some of the variables cannot be controlled directly, such as byproducts sometimes. You cannot remove them because of the fed batch nature of the bioreactor, because once you put things inside, you cannot take anything outside. So then you need some other variable to be controlled to control the other one. In this case, this kind of property becomes useful, and then there are properties such as edge weight, which will tell you what kind of an impact you have created by using a control action. So once we had this, we identified some set of new variables which are really important for these control actions. And once we had those new set of variables, it was important to actually use some data science concept for developing control models. So we moved on to doing data fitting. So based on the variables that we identified from these networks, I actually tried to predict what the outcome looks like. So I also used the variables that were found in literature. But then, as I said, the variables found in literature has a problem that they're not really universally applicable, and which really restricts their use. But then the variables that we identified worked across different cell lines, product types, as well as culture conditions. And they also performed better. And this is great, because at this point, we could just look at the variables, like look at the readings that we are taking, and see that, okay, this is going to be the outcome on that specific day. And then what we wanted to see was, okay, if we can predict what's going to happen today, can we also predict what's going to happen tomorrow? Because for a control action, we need that. So at this point, we did some forecasting. Basically, what we would do is predict the values of the variables for the next day, and then use that in the same equation so that you can actually predict the value of the output on the next day. So I basically used machine learning models and trained them so that we could get like really good predictions. And at this point, we had two things. One, we could look at the variables and tell what we had, what the output is going to look like today, and then we also had variable values which will tell us what's going to happen tomorrow. And this is a really powerful thing to have, because at this point, we can really develop a control model. So this is how I demonstrated the control. For a bioprocess control, I picked a culture, and then using the models, I predicted the expected value of the output at the next time point, which is like the next day. And then I introduced a small perturbation to a particular variable that's known to be detrimental. And then we use the same models, and then we observe how this perturbation affects the output at the next time point. Now, the objective was to actually see how this observed value can be converted into the expected value. We wanted to see, if there was an actual disturbance, can we change this and control it in some ways. So for this, I basically looked at the network and for each particular day, and then identified the best target variable based on different properties such as shortest path, weight, etc. And once we had that, I identified mathematical relationship between these variables. And once we have mathematical relationships, it's much easier for you to just use an appropriate optimization algorithm. And this will really tell you what needs to be changed so that the system would go back from the observed value to the expected value. So at this point, what we had was really powerful, because previously you could not look at the system and tell if something is going wrong. And if something was actually going wrong and you could tell it, there is no way you could salvage it because nobody knew what needed to be changed. But in this, by using this bioprocess control model, it will really tell you what the system is expected to do, based on what we learn from the data. And then it will also tell you if it's not going right. And if it's not going right, it will tell you which variable to identify and how much of it has to be changed so that you can actually salvage the culture. So the dynamic control scheme that I proposed, it looks like this at the back end, but what it means for a front-end user is that once you set up the bioreactor, you measure the variables for a time point t, and then the system would predict the outcome at the next time point, and then once you observe what's happening at the next time point, and if the observed value is less than the predicted value, the system would suggest a control action to be implemented at that time point. So what we achieve from this is that we have cultures with very less variability that follows a very tightly controlled trajectory. And this is important because a controllable system is an optimizable system, because if we can control the system, we can also control it to actually produce more. And once we have more productivity, we can also reduce the cost and make it more accessible to people. And that's how, that was my project, and it was just a prototype, but then hopefully it will work. This is a collaboration with AstraZeneca, so they're trying to test out in the lab. And I would really like to thank my supervisor, Duiku, who has moved to UCL since, and Professor Alex, who has been a really constant source of support, Dr. Aisha and Matthew from AstraZeneca, the PSC group, and colloidal dispersions from CB, and the G-Smart Bio from Biochemical Engineering, and AstraZeneca for the funding, CB for all the infrastructure support, and Churchill College for all the help throughout the years. Thank you very much.